Yesterday we began a new unit on probability, and today I want to explore the difference between experimental and theoretical probability. In order to best understand experimental probability, it's helpful to do an experiment. So I tried to think of a good way to do this with distance learning, and I was reminded of a funny thing I saw one time on The Tonight Show with Jimmy Fallon. So I have a pretty good experiment we can experience together on video, and then I have an experiment that you can try on your own on the next Nearpod slide. So if I wanted to know the probability, if I showed you some eggs, some of which are raw and some of which I've cooked, and I asked you the probability of randomly selecting an egg and having it be a raw egg, you would have no way by looking at these eggs to be able to calculate the probability of randomly selecting a raw egg. In the same way that you would have no way of calculating the probability of randomly selecting a cooked egg, because you don't know how many are raw and how many have been cooked. But what we do know is that each of these probabilities lands somewhere in the range from 0 to 1 inclusive. In other words, there are 12 eggs, so 12 possible outcomes if I randomly select an egg. And if none of them are raw, then there's a 0 out of 12 or a 0% chance of selecting a raw egg. If they were all cooked, the probability of selecting a raw egg would be exactly 0. It would be impossible. On the other hand, if they were all raw, if 12 of the 12 eggs were raw, then the probability of selecting a raw egg would be 1. It would be certain. You would be certain to select a raw egg. If exactly 6 of the eggs are raw, then there would be a 6/12 probability of selecting a raw egg. And there would also be a 6/12 probability of selecting a cooked egg. It would be 50-50 in that case. Now, the thing with the experimental probability is you can't calculate it because you can't tell which eggs are raw and which eggs are cooked, so you have to conduct an experiment. If you knew which eggs were raw and which eggs were cooked, then you could calculate the theoretical probability. And I know the theoretical probability of selecting a raw egg because I'm the one who cooked some of the eggs. Unfortunately, I don't remember where I put the cooked ones, but so that'll be a surprise for both of us. But let's conduct an experiment to test whether an egg is raw or cooked. We'll do our first trial. I'll randomly select an egg, and we'll see whether it's raw or cooked. That one's a cooked egg. I'll be eating that later. We should collect data from our experiment. We're working on the experimental probability of selecting a raw egg. So far we did one trial and the egg was cooked. Let's randomly select another egg from the carton and test it. That one is also cooked. Excuse me while I two cooked so far. Let's randomly select another egg from the carton. Test it. That would be a raw egg. I didn't think about where to put this. Put it right there. That was a raw egg. Excuse me while I clean up a bit. That one is raw. Let's test another egg. Randomly select the egg from the carton. Test it. That egg is cooked. So let's record that in our table. Now, if we ended our experiment there, our experimental probability, we could calculate an experimental probability of randomly selecting a raw egg because there was one favorable outcome out of 4 total outcomes. There was a 1/4 probability of selecting a raw egg, and we can see that there would be the complement, or a 3/4 probability of selecting a cooked egg. An experimental probability is often a good indication of the theoretical probability, but it is also, not only often, but most often, almost always, not an exact representation of the theoretical probability. The only way to know the theoretical probability would be to actually test every single egg. And so let's do that. If I select an egg at random, that's cooked. Another egg, cooked. Next egg, that one's also cooked. Another random egg. That's raw. Another egg, cooked. So I've got one more raw and one more cooked that I should have to enter in my table. I'm just trying not to make any more of a mess than it. Raw and cooked. Another random egg. Oh, that one's also raw. Another raw egg. Another egg. Cooked, thankfully. And the last of our 12 eggs. Oh, that one's raw. All right, now we have all of the data. And if you know the every single egg, then you can calculate the theoretical probability, because I know if I randomly selected an egg, there were 4 favorable outcomes and 12 possible outcomes, and so I had a 4/12 or 1/3 probability of selecting a raw egg. And as far as cooked, I had 8 favorable outcomes out of 12 possible outcomes, or a 2/3 probability. Now 1/3 is close to 1/4. It's not exactly 1/4, and when you're dealing with experimental probability, the experiment will approximate the theory, but will almost never be exactly equal to the theoretical probability. Of course, with the more eggs, if I had, instead of 12 eggs, if I had 12,000 eggs, the larger the sample size that we tested, the closer our experimental probability would be to the theoretical probability. And you experienced that when we did the goldfish lab, when we estimated wildlife proportions by using goldfish and doing several trials, averaging the trials, trying to collect the largest sample size possible. So this brings us back to these ideas that we explored when we were doing proportional reasoning. It's a very similar idea. If I show you the here are 12 eggs. I'm not going to crack any of these. They actually all happen to be raw, but I labeled them so you sort of get a visual. We started with 4 raw and 8 cooked eggs. So when you can see what they are, you can calculate it directly and get the theoretical probability exactly. But if you don't know, then you calculate an experimental probability by collecting data. By the way, this is something I used to do a lot when I worked in the semiconductor industry as an engineer. We would make computer chips on wafers, and each wafer would hold sometimes hundreds of computer chips, and we wanted to know how many of them were good and how many of them were faulty. And you can test a computer chip. It's not like breaking an egg. You can still use it after you test it, but it costs money to test it. So you can't test every single one. So you test a statistically significant sample size, like breaking 4 eggs, and then you get an idea of the experimental probability, or what we used to call the yield, what percentage of the computer chips yielded at an acceptable rate, because you don't want too many faulty computer chips. Otherwise, people are not going to think much of your company that sells computer chips, because too many people will be getting computer chips that fail out of the box. And so all of these ideas of probability are applicable and extremely important when you're doing any kind of endeavor. If you think of a population of the country, 300 and something million people, and you wanted to test for the thing we're going through now, the coronavirus, you can't test every single person, but if you test a statistically significant sample size, you can determine very accurate experimental probabilities and use those to guide public policy. I have an experiment that you can try on the next slide. It's not as messy, but I think it'll be fun. It involves flipping some cups. So take a look at that on the next Nearpod slide. Thanks.